So let me recap a little bit what we had seen. We started studying the high temperature and the low temperature limit of this XY model. But before I discuss the high temperature of the XY, before I recall, let me recall the high temperature of the Ising model. So the Ising model is this model here, and there's no approximation here. Because this way of writing it, where I have product over links in my partition function, rather than exponential of Hamiltonian is the same thing, because a product is the exponential of a sum. And this term here is nothing but the exponential of beta j sigma I sigma j. So this is just a way of writing this exponential that can take two values, because the product of sigmas is also either plus 1 or minus 1. So I can write it as a linear function that takes two values. So this is an exact equality. But then, when I think that this is a product over links, it means that for each link, I either take A or I take B. Right? I product over a link. So if I expand out, it means that for each link, I take an A or I take a B. Now, I have to be careful, because if I sum over sigma, because sigma is plus minus 1, the sum over sigma is 0. So if for a link, I take a B, I have a sigma, so I'm in danger of getting 0. So the only way I don't get 0 is if there is a neighboring link which also contains a sigma, because sum of sigma square is equal to 2. So it means that my partition function is given by loops. So whenever I have a link, it must close such that each sigma appears an even number of times. And therefore, either sigma doesn't appear at all, I take A, or if I take B, I better take a loop, otherwise I get 0. So what do I get? I get B over A to the power of the length of the loops. And I could have, for example, two loops like here. I hope you can see that this is two loops. Is it clear? By the way, after you draw the loop, this loop, you still sum over the sigmas that can be plus minus 1 here or outside. And summation of sigma I square, which is what you get inside the loop, gives 2. And summation over the links with A, which are empty, it's summation of 1, they also give 2. So there is a 2 to the number of sides outside. And in the lecture, I had put the 2 inside, because I forgot that outside there's also a factor of 2. So this 2 is here, and it's not here like in the lecture yesterday. Okay? In other words, there is a 2 for each empty link. I sum over 1. For each empty side, there is a 2. And for each side here, there is also 2, because what appears there is sigma squared. So for each side, there is a 2 independently of whether it's a loop or not. So it's really 2 to the number of sides and not 2 inside here. Okay? So please fix, there was a 2 that I wrote here, there's no 2. Now, in this representation, studying low temperature is pretty straightforward, because at low temperature is the regime where B over A, which is this tangent of beta j, is very small. So if B over A is very small, we want loops which are very, very small. And when I compute the partition function, you see I'm inserting a source sigma I and putting a kink sigma j, if you want, a sink sigma j, sorry. So there are already two sigmas, and I need an even number of them. So I need to expand the links, and I need to make a path between the 2 points, such that now sigma appears twice, one because I put it on another time from the link, and then everyone appears twice, and this guy appears twice, once from the link and once because I put it. And therefore everyone appears twice, and this contributes. And what does it contribute, this path? It gives me beta j to the length of the path. So in the low temperature limit, in the low beta, which is high temperature limit, what this gives me something like beta j to the power of the minimal length, and what's important, it's exponential decay. It's very small at large distance. For the high XY model, we had the same thing, except that, at least the way we wrote it, it was an approximation. So we expand down the exponential and we get this. This is not an exact result. This is an approximation at small beta. We could write it as an exact result. If I write here some very complicated sum with Bessel functions, there is a nice identity that allows us to make the analog of that first statement exact. And then instead of a loop gas, we have a generalized loop gas. But we are not going in that direction, so we don't care. So we are happy with an approximation here. And now that we have this approximation, by the same reason, we see that if I can take this term, this is the analog of A, and this is the analog of B in that example. But whenever I have a sigma I, a e to the I theta I alone, I'm in trouble because an integral of a single one gives 0. So I also need two exponentials, like there I need two sigmas. So when I compute now a correlation function of, say, sigma k, sigma l, this is like inserting in this integral e to the I theta k minus I theta l, right? But this guy cannot be alone, so I need to take this guy for its neighboring link, and so on. And therefore, I need to do a path such that each exponential appears twice, one with sign plus, one with sign minus, thus canceling and thus giving an integral which is non-zero. Right? So I'm inserting a plus exponential. So from this link, the first link, I pick the minus exponential that cancel it. And then from the next link, I take again this minus exponential to cancel that term, and so on until I get to the very end. And therefore, I get something. Well, in this case, there is a 1/2 here. So actually, in this case, there is a 1/2 here. I get beta j over 2 to the power of the length, again, between the two. And that's, again, exponential decay. Then we started the low temperature analysis, where at low temperature, large beta, we think that we should suppress these fluctuations. So we are trying to say that at low temperature, the angles like to be aligned. So we expand out the cosine and we get what I wrote there. But this is the model we solved already, and I've just summarized here some of the things. So one thing we could do, for example, is go to Fourier. If you go to Fourier, that sum over neighbors becomes diagonal. I just get a bunch of modes, all of them decoupled, all of them massless. Okay, all of them massless. Okay, sorry. It's one massless field, so it means that it has that the modes have this sine square plus sine square without an m squared term. So they are massless. And this is a Gaussian integral. That exponential is nothing but e to the minus 1/2, a vector with all thetas, then a matrix A, then a vector with all thetas. And the inverse is nothing but a propagator that we computed. Right? This was what we had seen. And this propagator, I just wrote it here. So a propagator coupling two lines, two thetas, which means ni and nj, would be given by this Fourier transform. Okay? So this is our propagator. And therefore, and now in this approximation, when I have exponent e to the I theta k e to the minus I theta k plus n or plus x, and this would be the correlation of s at position k dot s at position k plus x. This is just Gaussian integration that I can do, and I get that this is just exponential of the propagator at x minus the propagator at 0, where the propagator is given by that expression. Let's write it again here. G of x is equal to the integral. Actually, sorry, there's no L squared here. I already converted into an integral. Integral d2k over 2 pi square e to the I k dot x divided by sine square of k over 2 kx plus sine square of ky over 2. And I'm sorry, so there is a mistake here, which is I forgot the beta j, the normalization. So with this normalization, the propagator is, 1 second. So sine, okay, so there are a few things that I have to be more careful here. So there is a 4 here, a 4 here. Remember there was this 8 kappa. So at small k, this is just k squared. That's how I know there is a 4 when I normalize with a 1/2. So there is a 4 here and a 4 here. It becomes k squared. And therefore there is a 4 here. There is a 4 here. And there is the inverse of this coupling. So there is a 1 over beta j. Yeah. Okay. And right. So here there is a 4. Here there is a 4. And there is a 1 over beta j here. And this integral behaves at large distances it behaves as large distances as minus 1 over 2 pi beta j log of the separation at large distances and therefore at large distances this integral would behave as 1 over x to the power 1 over 2 pi beta j.
Sorry.
Yes.
Where can we see that behavior at large x?
So at large x, we are going to see it in detail soon. But this was, you also saw it probably in one of the tutorials. But one way of seeing it is you can analyze the small k behavior of this integral. Because when x is large, k needs to be very small. Now this goes like 1 over k squared at small k, right? K needs to be very small, so this is 1 over k squared. And this integral close to small k, if I go to radial coordinates, is k dk, right, in spherical coordinates. So in total, I get a 1 over k, and 1 over k diverges logarithmically as small k. And the cutoff will be related to the distance, and therefore there will be a log. Okay. So this is the behavior at large x, and so it goes to 0. But what's different is that we have a power law behavior. And we get a power law with a varying exponent. And this would indicate a line of critical theories. And so our summary was that perhaps there is a transition between these two regimes at some critical temperature where we have at very high temperatures, we have exponential decay. And we would transition to power law decay. And this would be a transition between the two. Okay, so that's the intuition. And the intuition was that what we were missing in this low temperature approximation was what happens as we approach here is that as we approach this domain, we forgot in this approximation the periodic nature of our angle theta of theta should become important. The fact that theta is really a periodic variable and that it can form these funny configurations like vortices that in our fluctuation analysis we were not really considering. And indeed, these vortices will be key in understanding this transition, and that will be the subject of Thursday's lecture. Okay, so yeah, so let me see. Here in my notes, yeah, it's it's a bit annoying. Let me check something. Yeah, so what sign did I choose for the cosine? Do you remember? It was plus or minus in the exponent. It was plus?
Yes.
Okay, then when I expand the cosine, I get minus there, so it looks okay. Okay, let's hope it's okay. So what we are going to do for the next half an hour, it's actually a little bit, it's not the most exciting thing physically, but I think it's important to give you some, because I think it introduces some mathematical ideas that are convenient. We are going to compute this logarithmic term very carefully. Okay, so what we are going to do, so I did a back to the envelope estimate that 1 over k, it's logarithmic and so on. I would like to compute this quantity very carefully and very precisely. So we would like to compute, the goal is to compute this exponential rather precisely. So what we want to do now is to compute this exponential of minus 1 over beta j integral d kx over 2 pi integral d ky over 2 pi. And then I put a minus here. There was no minus in the exponent, but that's because I'm going to write g of 0 minus g of x. So upstairs, g of 0 as exponential 1, and g of x as exponential e to the I q dot x. And then I'm going to write the sine squares in this way. The sine squares can be written as like this. I'm going to use one identity that I'm going to write. One of them, I leave it as is, for sine square, here it's k, of kx over 2. And the other one, I'm going to write plus 2 minus 2 cosine of kx. That's just the other sine square, ky. Okay. And this quantity here is defined as 2 pi gamma of x. And what we want to do is study gamma at x large. And the reason is that we will see that actually, if I study this gamma at x large, I will get an amazing approximation for gamma at all values of x. And that approximation is going to be convenient when I want to, when we will want to study the vortices later. But let me first emphasize a comment that what is hard is not to compute the logarithmic term. That is rather simple, but to compute corrections to this logarithm, which is what we are going to extract carefully. Okay, so we are going to compute not only the leading term, but the subleading term as well. And that's what's much more challenging to do. But let me mention that we are going to do it in a long way, as I said. But the shortcut to get this log is to just expand that small k. That gives me the log right away. Or remember that the propagator is the inverse of the discrete Laplacian, because it's the inverse of the matrix. So this propagator obeys, right? This propagator obeys that something like discrete Laplacian times the propagator equal to delta function, or because there is some beta, some 1 over beta j delta function, okay, at distance x. And therefore, you see that this G is like the electrostatic potential for a point-like charge in 2 dimensions, right? So this G, so this G is like the electrostatic potential for a point charge, right? So a point charge would generate an electric field that would be 1 over beta j divided by the distance that corresponds to, or if I have a 2 pi because when I integrate I should get the energy, which corresponds to a potential that would be minus 1 over 2 pi j logarithm of the distance, such that the derivatives give me this electric field. Okay? So just by recognizing that my propagator is the inverse of the Laplacian, is it clear why? No. Because the propagator was the inverse of the matrix A. And A, you see, it is just coupling between nearest neighbors. It's just the discrete derivative, just theta I minus theta I plus 1. So this propagator obeys the equation that A minus 1 ij dot this propagator between sides I and j and k, is delta ik.
Should that be aij rather than aij inverse?
Sorry, good point, yeah. So the propagator was the inverse of the matrix, right? And what is this matrix? This matrix is just a discrete derivative that takes derivative between neighboring points. So in the continuum limit, this is nothing but the derivative of theta square. I and j are neighbors, so this is just derivative in x direction square plus derivative in y direction square.
There's no. This might be a stupid question now, but there's no like. Is it because the lattice spacing is 1, or like there's no?
I'm going at large distances. So in practice, the lattice spacing is very small compared to the distance I'm looking at. So I did not introduce a lattice spacing. If I want, I could say this change slowly over lattice spacing. I divide by lattice spacing. I multiply by lattice spacing a square here.
Okay.
And this would give some more natural dimensions if I want to say things very slowly over lattice spacing. But choosing lattice spacing is my convention, right? I choose lattice spacing is equal to 1, so I don't put. And I really, at this point, I don't want to put. But you can say that you could put it there artificial. So this is just the derivative of theta square, right? So it's just box theta. It's just theta box theta. Right? So the inverse, the propagator, is just the inverse of the second derivative. But this is the equation. But this is the equation for an electrostatic potential with a point-like source. So if I think of gradient of G as being the electric field, that's just a point-like particle which has 1 over r potential and which has a 1 over r4 electric field and therefore potential logarithm. And that's just another way of getting the large distance behavior. So at large distance, this is one way of getting this log. Another way of getting the log.
Sorry, I still don't. Like, is this not what's in the exponential? Is that not the gradient of theta squared rather than the Laplace of theta?
Okay, so we would get the integral of, as you said, the gradient of theta square, right? That's what you're saying? Which is equal to the integral, integrating by parts, of theta Laplacian theta, up to a minus I. If I integrate by parts. And why do I like to write it in this way? Because in this way I recognize theta, a matrix, and then theta again. Okay. And this, or I have that. This is equal to this, where this A is a discrete Laplacian right away. because it's what is this matrix A? This matrix A is just a matrix that you see when I expand out that square, it's roughly 1 on the diagonal, 1, 1, 1, 1, 1, 1, 1. When I expand, I get theta I square, and I also get theta j square. And then the off diagonal term just couples the nearest neighbor. So there's like minus a half, minus a half, minus a half, minus a half on the off diagonal, where diagonal means same point and off diagonal means neighboring points. So up to some constant, okay, maybe minus 1 actually, because there are 2 terms for each. So up to, so this would be just a matrix that couples, no, I think it was okay, minus a half. It is just a matrix that couples same side with neighboring side. It really is the discretization of a second derivative. Okay, it's just couples. Okay, but this is, so again, so the point is that at large distances, we are inverting a discrete Laplacian, but at large distance, discrete or continuous doesn't matter. And therefore, because we are inverting the Laplacian, we are basically solving the differential equation that Laplacian times propagator equal to delta function. But that I think as gradient of G, which is the electric field. So the electric field would be 1 over R. And therefore, G, the electrostatic potential, would be logarithmic. And that's how I would get the logarithmic behavior in a very, another way of getting the logarithmic behavior. Okay, good. But what we want to do here is study this function here. And I will tell you what the result is. And that's our goal for that will take us a little bit. But what we want to show, so the goal is to show that gamma of x is very well approximated by logarithm of 2 square root of 2 exponential of the Euler number times distance x. Okay? And then, together with this 2 pi and this beta j, you see that the leading behavior is what I wrote there. But this is a correction to the leading behavior. Right? This would be a small correction. And if I say that this is x is the separation, I can think of this term as like a natural scale 1 over some r0. That would be the natural scale that appears inside the log when this log is relevant. And just to put some numbers there, this 1 over r0, okay, I don't have numbers here, but I'll give it later. Okay, so that's just our goal. And that's a very good approximation because, I do have it here, sorry. So this, if I plug here absolute value of x equal to 1, so one side distance, that's definitely not very large, right? And it's just one side, it's as close as it could get. This is 1.6169. Whereas gamma, the exact function, we will see, when absolute value of x equal to 1, it's 1.5708. And so even though the formula is asymptotic, it's amazingly good roughly everywhere. Because even for length 1, it's already as good. And it only gets better as the length becomes bigger. It only is a better approximation. Okay? So we are going to derive this at x large. At x large, we find this approximation. But actually, it works very well everywhere. Of course, it doesn't work well when x equal to 0 because it explodes. Whereas the exact result is 0 by definition when x equal to 0. Right? So this function gamma at x equal to 0, you see, it's defined to be 0. And that doesn't work there with the approximation because the approximation, this approximation is of course at large x. And even taking x equals 1 is, of course, something that it's nice that we can do, but a priori we are not allowed. But x equals 0, we definitely cannot. And we see from here that the result is 0. And that's obvious, because then when x equals to 0, this quantity becomes 1. But that's obvious, because at x equal to 0, I'm just computing the expectation value of s dot s at the same position, and this was equal to 1. Okay, good. So right. So my proposal now is to just compute this integral. And so let's do it. I think it will take us maybe 15 minutes. But I think it's good practice. It shows us some tricks that you might not be familiar with. Okay. I also thought it could be a homework. This could be the homework, but I thought it's boring, right? To compute an integral as a homework. I think it's useful. You will suffer a bit, and you could learn some tricks. So if you prefer, do you want to vote? You could. I mean, it's a very well stated statement. You can just believe it and compute it by yourself, and it could be the homework. And then I don't have to prepare a homework. Is this reasonable or not a good homework? It's too boring, right? Yeah, I think Alexandre would complain it doesn't have enough physics, and I think he would be right. Okay. So let's compute. So we compute the integral. So we take x. Let's consider x to be 2n 0. So I want to take x large, and I want to parameterize it in this way. So I chose to put it at an even side 2n 0. Because as you will see, it becomes a little bit more convenient. And in that case, my gamma at position 2n 0 would be equal. Well, then the exponential just depends on dkx. So it's nice to take out the exponential, 1 minus the exponential. And by symmetry, the exponential, I can write just the cosine part, because the sine is 0 when I integrate between minus pi and pi by parity. Okay? And I put, I don't know, I put this, there's nothing. And then integral d qy over 2 pi 1 over what I wrote there for sine square of kx over 2 plus 2 minus 2 cosine of qy. No, sorry. In my notes, I'm using q, so I'll do this mistake several times, I believe. ky. Okay. So you see that this is an even function of kx. So here, when I add the exponential, I have cosine and sine, but the sine is odd, so it doesn't matter. When I integrate from minus pi to pi, it would be 0. So I have this object that I have to compute, and this is nothing but sine square of n kx with a factor of 2. And this integral that I have to integrate between minus pi and pi gives me 1 over, and I will explain why, but let me write the result first so that we understand the steps we are doing. It gives 1 over square root of 4 sine square of kx over 2 times 1 plus sine square of kx over 2. That's the result it gives. So let's explain why this integral gives this. So one idea for doing this integral that I think it's convenient to know is when we have these integrals we are integrating over ky. So a nice thing we could do for this integral here, to do this integral here, is using complex analysis, define e to the I ky. I define this as being y. Right? And then what am I doing? The integral from minus pi to pi dky is just the integral, it even has a 2 pi, which is nice, over 2 pi, is just the contour integral dy over y times 1 over 2 pi I, where this contour integral is over absolute value of y equal to 1. Okay? And what is this cosine here? This cosine, now that I have a contour integral, what is this cosine? Under this change of variable, this cosine is just 1/2 of y plus 1 over y. Right? That's what cosine is. And therefore, notice that because it's y and 1 over y, when is the denominator 0? So because it's y and 1 over I, we see that the denominator vanishes at some value y star and 1 over y star. Because whenever y star is a solution, 1 over y star is also a solution. Right? Because if the denominator is 0 at some value y star, when I replace y star by 1 over y star, cosine is invariant. Right? Which means that this integral here, I'm computing an integral dy 1 over y minus y star, y minus 1 over y star, because you see I multiply over by the y, and I'm integrating over absolute value of y equal 1. So one of them will be inside the unit disk and the other will be outside. So this integral would be just, I compute one of them, 1 over y star minus 1 over y star. Okay? So this is just one of the residues, because the other one is inside, one is outside. So I choose either to blow or to shrink the contour, it doesn't matter. I pick one of the poles, and that gives me the result. So all I have to do is compute this 0 of y star. I compute, it's a quadratic equation, and when I solve it, I get the square root. Good?
Sorry.
Yes?
You also have the y that comes from the measure, like...
Right, so this dy over y is such that when I multiply the denominator by y, it kills this 1 over y and makes it a nice polynomial of degree 2.
Yeah.
Is it okay? That's why the denominator is a polynomial of degree 2, and therefore it takes this form. Precisely because I multiply by that y, such that there is no 1 over y downstairs. So this 1 over y looks dangerous. This 1 over y in the cosine looks dangerous. When I multiply by y, I cancel this 1 over y, and I get y squared and y times that term there. So everything is just a polynomial downstairs. Okay, cool. So at this point, we already got rid of one of the integrals, so that's great. So we go on, and now I'm going to separate it. So what do I get? So look here with me. I get 1 over this term, and I'm integrating between minus pi and pi. Right? Can I take out this? This looks like a perfect square. Can I take it out? Outside, can I write 2 sine and take it out? Well, I need to be careful, because this is always positive, and if I take it out for k, if I'm in one region or the other region, between minus pi and pi, if I'm in for negative or positive, I would get a different sign. So I can take it out if I replace this integral by twice the integral from 0 to pi over 2, and then I can take out here I can take out twice sine of kx over 2 from the square root. So when I do it in total, I get the following. So look here with me because I'm going to write it next. So a 2, a 2, a 2. So in total, I will get a 2 outside. And what will be inside? Sine square over sine, and then 1 over square root. Right? So 1 over square root is complicated, but the important behavior is for k equals 0, where 1 over that square root is just equal to 1. So I will separate the square root, add and subtract 1, because at small k this remaining square root is 1, such that I analyze properly the important behavior. So in total I have a 2, as I said, integral of the remaining variable that I will call q, and I will also do at this point a rescaling. I will call qx equal twice q, such that the integral, instead of 0 to pi, it goes from 0, sorry, here I said twice from 0 to pi, right? It's the upper part, it's the positive part, but now I wrote it as 0 to pi over 2 in this rescaled variable. And then what I get in this rescaled variable is sine square of 2nq divided by sine of q. Sorry, here I did kx equal 2q. Plus sine square of 2nq divided by sine of nq times 1 over square root of 1 plus sine square of q minus 1. So all I did was I subtract 1 and I add 1. Okay. Now you see that when n is very large, this term here is going to be an interesting term, as we are going to see. Because when n is large, I'm forced to zoom at small q, and this will have a 1 over q behavior, and therefore this will be where the logarithm is coming from. So, whereas this one, sorry, there's no n here. When q is small, this term is designed to vanish as q goes to 0. So this term actually is regular, and this term only contributes to the constant term. So we are isolating. The log comes from here. Log n comes from here, as we will see. And from here, this will give just a constant at large n. Okay, so let's go on. So let's analyze now both terms separately. So this term, I'm going to write it as sine of 2nq. And the remaining sine of 2nq over sine q, I use a trigonometric identity just to write it as a sum of cosine of 2s minus 1 times q, where s runs from 1 to n. Okay, I just want to give you the general idea. So this is just, I write sine over sine. That sine over sine can be written trigonometrically like this. And now I just have a product of two trigonometric functions that I'm integrating. So this we know how to integrate. And therefore, this term, after integration, this here, gives me twice sum up to 2n minus 1 from s equals 0 of 1 over 2s plus 1. Okay. This is no approximation so far. And now comes the first approximation. So until now, no approximations at all. And now let's do the first, no, not yet. We are not, no, so far, okay, it's the same. So far, no approximations. So this is the contribution of this first part. It gives me this. Can you still read if I write here? Can you still see? No? But this you can, but not what I'm going to write next, right? Okay, so I'll move up here. So I'll continue up here. So this term is what? I'm summing over odd integers up to this value. So I can write I sum over everyone and then I subtract the even numbers. So let's do that. So if I sum over everyone means I sum twice. I sum over, what's the last integer? When I put here 2n minus 1, I get 4n minus 1 from s equal, and the first one when I put here 0 is 1. 1 from, let's put here k, say 1 over k. This is all integers. But we have to subtract the odd integers because this was only the even integers. This was only the odds. So what we want to do is subtract twice the even ones. The even ones I can put twice k, and I sum from k equal to 1 up to 2n minus 1, 1 over this. So this so far no approximation, but the advantage now is just the 2 cancels, and I'm just dealing with sums of 1 over k. And Euler, so now here we use Euler, told us that there is this very nice identity that when I sum integers 1 over k up to some integer n, this is equal to logarithm of n, like I'm integrating, plus this constant that's called the Euler constant, plus order 1 over n. Okay? And that's the definition, if you want, of this Euler constant. It's how the sum over integers up to n deviates from logarithm of n. Okay? So that's the definition of this Euler constant, which is something like 0.57. Okay, so we go on here. And therefore, that first term that we are studying is giving twice that sum, and that sum is giving log of 4n minus 1 plus Euler constant. So let me write it like this. And then the second sum gives minus log of 2n minus 1 e to the Euler constant. And that's approximately equal to, we put this inside for simplicity and then we divide. So this gives me 16n squared over 2n, so log of 8n e to the Euler gamma. Okay, and the first term. Okay. What about the second term? So the second term, what we can do here in the second term is we notice that because this is regular, if I want to approximate the second term, the clever trick here is to notice that we can replace the sine square by 1/2, where this 1/2 is just the average of sine square. The function oscillates a lot, and therefore I can just replace it. It's a very good approximation to just replace it by its average. In other words, if I write this as 1/2, which is the average, plus fluctuations, then the fluctuations would have both positive and negative sign, and they would be washed out. Again, this is equal to sine 1/2 plus something with both signs, and because it oscillates very fast, it just cancels out. And this is a good approximation because it multiplies something that is totally smooth. If the rest was not smooth, like here, I could not do this approximation because of the small momentum region. But because now we separated the dangerous part by adding and subtracting, this is a good approximation. So we replace it by 1/2. And then the second step that we do is this is a binomial coefficient. It's 1 plus sine square with a power that is just not an integer. But this we will expand using Newton's formula, so like a binomial. It's just the expansion of a plus b to some power n. And therefore, in total, so let me just write what we get from the second term. So the second term would be equal. The expansion that I said would give me a sum from s equal 1 up to infinity. Then the analog of the binomial coefficients are now gamma functions. Gamma of 1/2 of gamma 1/2 minus s factorial. That's just the expansion of that binomial coefficient. It starts at 1 because we subtract the 1, so there is no term 0. And then integral dq from 0 to pi over 2 of sine of q to the power 2s minus 1. So here, what we did was those two things. We replaced by 1/2 this average, and we expanded the sine square because now it's totally regular.
Sorry, what do you mean to expand the 1 over square root like a binomial?
So whenever you have 1 plus a to some power n, right, you know how to expand it. You know it's Taylor expansion, right? It's 1 plus n times what is there plus n minus 1 over 2 times what's there plus dot dot dot. So those n and minus 1 over 2 and so on can be written exactly like this. This is just a way of writing those terms. If this power 1/2 was a positive integer, this would truncate and it would be the expansion of the binomial. When it's not an integer, this doesn't truncate. It's an infinite sum, and that's just the expansion. So this here is just expanding 1 plus s squared to the power minus 1/2, right? So I can write this 1 minus 1/2 s squared plus s to the 4 over 8. So these coefficients there, they have this closed expression, which is just the analytic continuation of what I get if 1/2 is an integer. Yes?
How do you know that these subliving corrections are still isotropic?
Yeah, that's a good question. No, we don't. This is just an approximation. We know that at large distances I should get isotropy, and I can just then go and check. Once I have a prediction, I can just go and check numerically, and we see that already at x equal to 1, it's very good, and it's only going to get better. So it's going to be very well isotropic. It's very well approximated by isotropic. So the question Alexandre is asking, why am I considering x in this particular direction? Am I not worried that if I want the subliving corrections, I should consider all possible directions? But you could worry, and you could then check that all directions would give the same, and that would be the case. Okay. Now, this integral over sine, it's again an integral that you will know how to do. And in total, when you do this integral and put everything together, you will just get a sum of pi over 2s. And of course, you are I'm doing it quite fast just because it's just mathematics. I want to illustrate some tricks, but not the algebra itself. The algebra is boring. What I want to maybe emphasize are all these tricks of expanding things, replacing by averages, using this Euler definition, and so on. And then we get this. And then what is these functions? These new functions gamma we get just by integrating this sign. This is a function that has poles at the negative integers when the argument is negative integers, but we shift by 1/2. So this has poles at 3/2, 5/2, and so on. And this one as well in the opposite direction. So this is just a function sign. This is just actually sign, right? And at value s pi, it takes -1 to the s. I'm going to write it and then explain again a bit more slowly. So this is sum of 1/2 -1 to the s over s. That's just so I'm using here that I'm using the fact that if you take this expression and make full simplifying mathematics of this expression, it gives you something like sine of pi s over 2 minus over 2s. This expression is equal to that. That's just an identity of these gamma functions. So when s is 1, it gives me, is this correct? Sorry, let me check. So when s is 2, it gives me 0. It's not correct, sorry. When s is 1, it gives me 1. When s is 2, it should be what? Okay, so this is a function of the sine of pi s. Yeah, this is just cosine of pi s. And cosine of pi s is -1 when s is odd and 1 when s is even, so it gives me just -1 to the s. But that equality is true for any, this is true for any analytic s. And I get this expression, but this is just -1/2 logarithm of 2. So that's what the second term gives me. And if I put them together, I get that in total, gamma is log. You see, I have to divide by square root of 2. So 8 divided by square root of 2 gives me exactly 2 square root of 2 exponential of Euler gamma x. Which is what we wanted to establish. Okay. Yeah. Okay. Yes?
The previous result was in terms of n, right? And n is x by 2.
Yeah, hopefully I converted. And let's see. Let's see if it works.
Yes.
Let's try. So 8. So this
8 by
is 4 times the distance, right? And this is 2 times square root of 2 times square root of 2 times the distance. And I divide by square root of 2 and I get 2 square root of 2. Okay. Okay. So the conclusion here is that, let me do it here. What we did is we had this approximation and we have now a slightly better estimate that this is equal at large x to r0 over distance to the power gamma, where gamma is a critical exponent 1 over 2 pi beta j. It's a critical exponent. And this R0 is just 1 over 2 square root of 2 e to the Euler gamma. It gives you an idea of this length scale. And that's a better approximation. Okay. So that's it. So now we would like to see evidence for this crossover behavior between these two regimes. So what we would like now to discuss a bit is the importance or not of vortices. So vortices would be these configurations where basically my theta is approximately equal to n times some angle phi. This n could be plus or minus 1 or plus or minus 2, etc. But the simplest case would be plus or minus 1. That is, if I'm looking far away, this is some far away distance, and I'm changing phi, the angle theta would change continuously like this. And there are many sites here. So at each site, the angle changes very little. It changes by 1 over n, this side. So this here, it changes very little. So the variation of my angle phi here would be something very small. The derivative of when I'm very far away. And we can estimate the energy. So let's estimate the energy of a vortex. And this estimate will tell me that the vortex would be something like beta j over 2. And I would integrate this over the integral in radial coordinates, so something like 2 pi r dr. And then the Laplacian square of my angle, that would give me something like n over r square. Say that the derivative there would vary like that. So let me just open a parenthesis that rigorously we would like to solve to find some equation box theta equal to 0 that would have this profile, some classical configuration where theta behaves as n phi at large jar, and then plug that solution into the action and see how much it contributes. Okay, so we are going to do it in the next lecture, but for this purpose we are just estimating the order of magnitude of the energy of this vortex. So what I'm doing is fine. But in practice, that's what you should do. You say that if these vortices are important configurations, there should be solutions of the classical equations of motion that have this vortex profile. And I plug them into the action to see how much do they contribute. Is it reasonable to expand the action around these solutions as well? Okay. So, and indeed, you can find these solutions. They exist. I could even write them down. It would be something like theta equal n times some arc tangent of x minus the position where it is divided by y minus yi. I think it's something like this, but I would have to think more carefully. And these solutions will indeed, far from the center of the vortex, this would be the center of the vortex, they would indeed just behave like this, and they obey Laplace equation on the plane. So these would be solutions of Laplace that would correspond to a vortex at position I. Okay? But okay, don't quote all the factors numerically correctly here, because this is good enough. And where do we integrate this? Well, up to the length, up to whatever size I have in my system, and starting from some a that is bigger than 1. What matters is this large distance, so there would be some scale here, a, and I integrate after some a of order 1, because the energy in a region of order 1 is always of order 1, so it doesn't matter much. But then this is logarithmically divergent, so this gives me, let's say 2 pi cancels that 2, it gives me beta j pi n square. N is what we call the charge of the vortex. It's how many times the angle winds as I go around. So the smallest ones have n equal to 1. And then the integral would give me logarithm of my size of my system in over A. Okay? And what matters is, of course, the upper limit, and it gives me beta j pi n square logarithm of the size. And therefore, this is huge, which implies that we can ignore single vortices in our lattice. So a single vortex would cost a lot of energy that would scale with the size of the table, and it should be ignored. It's really a very energetic configuration. Yes?
I don't understand the first expression of the energy of the vortex.
It should be noted.
Sorry? This is just how much the angle is varying.
Yeah.
And the angle, it is just n times phi. And so as I'm taking the derivative in radial coordinates, the variation is becoming smaller and smaller as I go to larger angles, because when I integrate, the total variation must be equal to 2 pi.
And it goes squared because it's like a kinetic energy?
Exactly. It's del phi square. So that's just the estimate of plugging this into del theta square. Okay. Just a computation of del theta square when theta is phi at very large theta. Okay, so we conclude that one vortex would be suppressed. But the point is that actually, if you have, the question is, what if we can have several vortices with zero total charge? And indeed, you could have vortices that have zero total charge. Then it means that very far away from the vortices, you see nothing, because one vorticity is absorbed from one vortex to the other. So the point is that one vortex is like a topological object that I cannot unwind this theta profile. But if I have two vortices, I could have a vortex with n equal +1 and the vortex with n equal -1. And here, far away, I could have thetas all pointing in the same direction. No problem. So I would not So the upper limit would not be the size of my table, which is L. It's not really the size of the table L that matters for the energy of these vortices, but the separation between the vortices, say L0. And now the idea is that the energy, now we ask if these configurations could be favorable or not. So we want to compare the energy with the entropy, like we had before when we were estimating if who wants to win, to see if the model likes to create these vortices in pairs, anti-pairs, if they like to create vortices or not. So the vortices cost energy, but on the other hand, I can put the vortices in many places, so they have a big entropy. So the energy, as we were saying, would contribute with minus beta j. Sorry, the energy doesn't have a beta. The energy is just the energy. It's just this. The energy is just this. The energy is just this. But when I'm computing the contribution to the yeah, the energy is this, J, yeah. But when I compute the contribution to the free energy is minus beta times the energy. So the contribution to the free energy is minus beta J pi log of this L0 over A. But the entropy would be, where can I put these vortices? Well, I can put them at some position. So there would be some position. And for each vortex, I could choose some positions here inside some domain of length L0. So there would be like order L0 squared for one, order L0 for one, order L0 for the other. So in total, there would be order L0 squared positions for where to put the vertices, for where to put each vortex. So for each vortex, I would have this energy and this entropy, right? For each one, I can choose where to put it. And therefore, when we compare both, so this is twice log of L0, we see that in total, we get log of L0 times from the entropy minus beta J pi, and from the energy this, and from the entropy 2. And so we see the critical temperature. We see that if beta is bigger than beta critical, which we are estimating here to be twice over J pi, then the energy suppresses. So if beta is this large, the energy wins, and this suppresses vortices. But if beta is smaller than this beta critical, then the energy is not so strong and the entropy wins. Then the entropy wins, and we expect to have a gas of vortices. Yes?
I don't understand the factors of beta. Like, why isn't there beta in the energy of the vortex? And why is there, like...
So, if you remember, so Z is the sum over configurations, right? E to the minus beta times the energy of that configuration. So the convention is that what I call energy is without the beta, right? Beta is the temperature.
This energy has beta.
Yeah, so here I'm, yeah, sorry. So yeah, this was sloppy, sorry. Energy contribution to free energy. It comes with beta times energy. It's minus beta times energy, right? So this is minus beta times energy. It's how the energy contributes to the free energy.
Okay, and just to remind me again, it's just where you're checking where this is positive and negative.
Yeah, I'm just checking who wins, because it's what we said last time, that this was, I'm summing, and I have e to the minus beta times my energy, but then I also have plus logarithm of the number of states, which is my entropy at that energy, and I have to check who wins to see where at the saddle point. So do I want to have more entropy? Entropy is good. Low energy is also good, and I have to see who wins. And indeed, we just see who is bigger. Is it the energy contribution or the entropy contribution? Okay, good. So now let's see that this is in line with what we had said before. Because beta bigger than some beta critical, this means temperature smaller than some critical temperature. So this would be the low temperature regime. So what we are saying is that if we go to low temperature, forget about these vortices. But if we forget about the vortices, we did the computation. It was this Gaussian model. Okay, so at low temperature, we forget about the value, and the Gaussian model should work. The Gaussian model should be okay. And at the Gaussian model, we got that the correlation of my spins was just 1 over the distance to the power 1 over 2 pi j beta. When the entropy wins, I have a gas of vortices. So my approximation of saying my field theory approximation of this Gaussian model is just not good, because it's not good to expand around all theta's pointing in the same direction, because I have this gas of vortices where theta's, they also like to form these configurations, these spiky configurations all over. So it's very wrong to just say theta's are roughly pointing up plus small fluctuations. That's just totally wrong. So here, when we have a gas of vortices, this Gaussian approximation is not good, and we will get here our gap phase with exponential decay. And then the transition is a transition between between this medium containing these vortices or not containing these vortices. And when they contain the vortices, the theory becomes much harder to describe. And when it doesn't contain the vortices, then we got this critical behavior. Yeah, no, good. It's very good if you ask questions.
Just to check what you're saying there, does the gas of vortices imply the exponential decay that we found earlier, or are you just saying that these two things must be?
They must be. So here we are, yeah, we did, this would be, it's not obvious yet, right? Why does the gas of vortices lead to exponential decay, right?
Okay.
I'm saying Gaussian is an approximation, and I said not good approximation, you need to add the vortices. Now, the statement that adding the vortices leads to exponential decay, it's not obvious, but it's a statement. It should be. For the picture to be consistent, it better be the case. Okay? And by the way, let me just notice that if we trust this hand-waving argument at the critical temperature, you see that beta is 2 over pi beta. So we would conclude that spin at the critical temperature, really at the transition, would be 1 over distance to the power 1/4. So this would be, just based on this hand-waving argument, a guess that at the critical temperature, this would be the behavior. And we are going to see in 2 lectures, if we are lucky, for example, that this guess is not bad. It's a good guess. In the sense that it's not exactly correct, but almost correct. And the spin at the critical value is indeed 1 over x to the power 1/4. But there are some logarithmic corrections. Log x to the power 1 over 8. So it's almost correct. So this is really the correct result. And this log, you can see that some effect of the vortices. They are barely disappearing. They almost disappeared completely, but they still left some remnants, and they corrected a little bit by this extra log power. And we will see in the very last lecture of this XY series where this comes about. That's probably the hardest computation we are going to do in the course. Okay, so it's not bad. So we are starting to get a picture that is fairly correct.
Are we almost everywhere dropping the characteristic length R0? Or does it disappear?
No, actually, if I were to write it more correctly, here x would be distance divided by R0 in this formulas here. But that's when we want to be extra careful, and here as well. But here it will be just normalization. Yes.
So you just focused on vortex anti-vortex pair of charge 1. What about higher order charges? It seems that your critical temperature will depend on charge.
Okay, very good. So Andres is asking, what if I have higher charges here? I could put some n square here and say that the vortex would have higher charges, but they would give an estimate of the, so the vortices, the first vortices that appear are the ones with charge plus minus 1. Then, if I increase further my temperature, at some point it becomes favorable to create vortices of vorticity 2, and then 3, and then 4. That's already in a regime that it's so hard to compute anyway that, you better forget. So you start slowly as you increase the temperature. First, the lowest energetic vortices, the one where the angle changes by 2 pi appear, then the ones where the angle changes by 4 pi, and so on, but indeed they would appear. And this would give us an estimate at which temperature would those vortices appear.
The thing is, what prevents single vortices?
Single vortices, they are prevented because their energy, their energy would be very large. They are not screened in any way. Their energy scales with the size of the system.
So does the entropy, no?
So does the entropy for a single vortex. That's a good point. But right, so why don't we like just a single vortex? Let me think. So naively. Yeah, I'm confused. I know it's because the entropy does not, but I agree that I'm. So let me think. Okay, let me summarize. So what we did here is we said that can we have vortices, and we estimated the contribution of entropy and the energy of vortices, and we saw when vortices should start coming in. The argument of why one vortex is never there was not very good, now that I realize, because indeed the entropy would be big. I think it must be that the boundary conditions for one single vortex to exist must change smoothly at the boundary of the box. And probably it would happen if I prepare a magnetic system where at the boundary I change the angle by 2 pi, then the only configurations inside will have an odd vorticity, and you could add one vortex plus an even number of them. But if the boundary condition is everyone up at the boundary, then this vortex cannot be as close to the boundary, and therefore the entropy is more about putting the vortex in the middle, and I think that would cost much more energy.
Can you phrase it also in terms of the fact that there's no spontaneous symmetry breaking? That you need to have vortex anti-vortex pair precisely to preserve this symmetry? If you just have one vortex, in a sense, you're breaking the symmetry now.
I don't think so. I don't see it that way. Okay, so no, that I don't see right away. But maybe you're right. You should tell me why do you think like that. So let me just then conclude with what was the physical picture here. So here we started asking, could these configurations where theta changes slowly, right? So the derivative, right, would be 1 over r times the variation of the angle. So it would be 1 over r. And therefore, the energy scales like 1 over r squared. And it gives me a logarithmic contribution. And we ask, could these configurations, they also look smooth. If I look locally, the angle is changing smoothly. But globally, they give me these logarithmic objects that have this big energy. So could they appear? And we see that, yes, it seems so. It seems like if the temperature is high enough, that is, if beta is small enough, because of this entropy contribution, the system would prefer to create these vortices. So these vortices then, you can think of them that the vortex can have vorticity +1 or vorticity -1, or 2 and -2, but those are much more energetic. So let's say just 1 and -1. And therefore, when you put them together, they when you put when you create yeah, okay. I remember now the answer to Andre's question, but okay, I'll finish what I'm saying now. So so when you create this still thing. Yeah, I think it's correct. Check. Yeah. So when you create these vortices, they will then interact with each other. They will start interacting the vortices with each other. So they form a gas of vortices that can have charge +1 or -1. Okay? So, and then you are studying a gas of particles that have charge +1 and -1 that interact with each other. And you start seeing where this Coulomb gas that I said this XY model is related to. That's exactly the gas of these vortices. And now what can happen when I have these particles that half of them have charge +1 and half have charge -1? So what happens if you put a bunch of particles, some of charge +1, some of charge -1 in a big box? You could very easily imagine two materials that could form. What could happen? The most natural scenarios is a charge plus likes a charge minus and forms some molecules, right? Some neutral states. That's one option. That would be what we would call a dielectric material. That would be a material which would be neutral. They just form these charges, tuck, 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 tuck. They form these bound states, so you don't see anything special. That's like air, right? We are in air, and electrons and protons, they are together. And okay, nothing special, and we have power law decay. The other thing that can happen is that the temperature could be so high that these charges don't have time to form these bound states, and they are all crazy moving around, and plus and minus charge are not connected to each other. That's what we call a plasma. That's when the charges are all chaotically moving around. But plasmas, what is a plasma? Plasma is something where you have availability of plus charge and minus charge everywhere. So you take your object, which is say a plus charge, and put it in a plasma, and immediately minus charges will come and surround it. So correlations between particles in a plasma, because of this screening, because you have available particles that go and screen, would now decay exponentially. And that's the picture on the high temperature side. So the low temperature, high temperature side is a transition in the plasma, in the gas of vortices between a dielectric material, where correlations are power law decay, like in air, and the plasma, where we have screening, and therefore correlations are exponentially suppressed. And that would be another way of interpreting this transition.
Can you make crystals of vortices?
Well, here they move freely, but you could ask if I could have more than 2 vortices, like 3 vortices, for example. So a 3 vortex contribution would happen at much higher energies, where I start having more vortices. But I don't think they would form crystals, no. At least not as far as I know, yeah. Okay. So tomorrow, what we will do is we'll start saying, okay, if we can have these vortices, let's write a classical configuration like this, that is a sum, or on Thursday, that is a sum of vortices. I put many vortices. I don't know what their position is, but I put a gas of vortices. And I will expand my action around the configuration that contains this gas of vortices. And then we'll study what is the effective theory that I get for the centers of these vortices. Where do the centers of these vortices like to be? And then we will study that statistical model, which is the model for a gas of vortex.
Can we derive the existence of vortices from the initial partition function that we consider? Or from the equations of motion or something?
But this was a derivation, heuristic, but it was a derivation. We just said that these configurations will exist. They will have some entropy, they will have some energy. So in the partition function, we show that these configurations will matter or not to the partition function.
But if we are analyzing a model that we are not sure, or we don't have a lot of physical intuition about it, how would we?
Yes. Okay, so a question is, can I mathematically, without any physical intuition, start with our starting Z and do equal dot 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 equal, and then boom, I have a partition function that looks like a vortex partition function, right? Without thinking. So that you can do, and you can do very cleanly in a modification of the model, where you replace the original Boltzmann weight, which was e to the minus beta cosine theta. You do a small modification that once you plot it, it looks exactly the same periodic function, but with just a slightly different function. And with that slightly different function, you can derive all these gas of particles analytically. And that we are going to do on Friday. On Thursday, you play with the model, with that model on the tutorial. So in the tutorial, you are asked to study a variation of xy that you will see the Boltzmann weight. It's clearly in the same universality class, but which allows this to introduce this gas of vortices analytically. So we will see that at work on Friday then in more detail. Okay, thank you.